Right. Ladies and gentlemen, hello there. Class, we're going to talk about the work energy theorem. We talked about this in lecture. Now let's go ahead and look at some problems that will interact with that. So remember, we got these list of equations here. So we got work is equal to change in kinetic energy. Now work is actually MAD, and we may have to put the cosine of theta in there, but for most of these problems, we don't have to worry about that. Kinetic energy is 0.5 mv squared. But the change in kinetic energy that we really need is actually 0.5 times the mass times the change in velocity squared. And I'm missing the square there. Sorry, that's my fault. So let's put a 2 there. And that's equal to this. So if work is equal to the change in kinetic energy, then the force, which is mass times acceleration times the distance, is equal to 0.5 mass. And there's the difference in velocity squared, which is our change in kinetic energy. This is where the change comes in. Now, mass is going to be the same thing. Now, here's the thing. I want to point out something that if we're looking for mass, that means either this is known or kinetic energy is known. So this is why we don't want to eliminate mass at this point. So let's look at the problem. We've got a hockey puck. Oh, we have an initial speed. There's VI. And it goes to 45 minutes. There's our distance. To a stop, VF is equal to 0. Now, if the force of friction on the puck has a magnitude of 0.12, what is the puck mass? Now, here's the thing, guys. So work is equal to force equal to change in kinetic energy. So we want to know what the change in kinetic energy is. We can find this right here. Now, the work is force times distance. Now, here's the problem. This force that's acting on the puck. So as the puck is moving, if it stays at the same speed, there's no change, there's no work being done, but it's slowing down. So the force that's acting on the puck is this magnitude of 0.12 newtons. It's going the opposite direction of what the puck is going, so it is going to be negative. So let's go ahead and put all this together. So force is equal to 0 minus 0.12 newtons. Distance, we'll get to there in a second. VI is 8.0 meters per second. VF is going to be 0, and this is going to be important a little bit down the line. Now, distance is 45 meters, and this is meters per second. And so what we're looking for is mass. So let's look at this. Work is equal to the change in kinetic energy, and what we're going to do is take the angle theta is going to be 0 or minus 180. Or 180 degrees. Doesn't matter. Both every time we look at this, it's going to be 1. So what we're looking at is that the work, which is force times distance, we have force, we have distance, is equal to the mass, 0.5 times the mass times the VF squared minus VI squared. We're looking for mass. Now the force is going to be minus 0.12 times the distance, which is 45. And actually, if I think about it, let's do the cosine of 180. That should be minus 1, because if we look at this, 0.5 times the mass, and the VF is 0. So that's going to be 0 minus 8 squared. So, well, there's our negative. Okay, so what we have now is a negative 45 times 0.12. Which is negative 5.4 divided by 0.5, and that is then divided by negative 8 squared. That's going to equal the mass. Now, these negatives are going to cancel. So 5.4 divided by the quantity 0.5 times 8 squared. you're going to get a mass of 0.169 kilograms. That's going to equal a mass, or 169 grams. And so that is how you work these type of problems. Realize when to use force times distance or mass times acceleration times distance, and when to use this. And now remember, the negative sign, that we're 8 squared, and that 8 is being subtracted from 0. So we realize that when we're doing this, you don't change this to positive yet. It's going to have to cancel this. So be very careful when you're doing some of these problems, because the negative signs do matter. If you have any questions, let me know either during Scott time or after school. Thank you.